Hello, in this installment we're going to start to learn about the electrostatic force, or FE. So where we are in the course, of course, is mechanics and kinematics and dynamics and conservation of momentum, conservation of energy, and then forces, which could be used to explain those. We've seen before we have some geometric cases, inclined plane and centripetal or circular motion. But the force we're looking at today, the electrostatic force, is really here. And so let's begin this conversation by the nature of electricity. All electricity proceeds from the behavior of elementary particles. And those elementary particles, of course, are protons, neutrons, and electrons. And we know this arrangement of the atom, which was perhaps first called the Rutherford model of the atom, followed by the Bohr model of the atom. But what's curious is at the time, even for Rutherford and those around, they didn't want to accept this planetary model of the atom because there were a couple things that didn't make sense. They defied the laws of physics. The first of those was that if the protons are all concentrated in the center, they should repel each other and fly off. So it doesn't make any sense for them to be concentrated in the nucleus, which is what he found. So the prior model, the plum pudding model, where the positive charge was distributed throughout the atom, actually made more sense. It was only when the data seemed to indicate that the positive charge was concentrated in one location that they deviated from that model. It made more sense. So the Rutherford model at the time made no sense because the protons should repel and not be found concentrated in one area. So that was the first reason the Rutherford model was very problematic. The second one had to do with something called synchrotron radiation. Now we already know that an electron traveling in an orbit has a velocity in this direction and has a centripetal acceleration if we're using a planetary model. Well, it was well known that if you have charged particles and they are accelerating, they give off radiation. They give off radiation, and that radiation is energy. So what should happen over time as a charged particle is undergoing centripetal acceleration around the nucleus, it should be giving off radiation, losing energy, and should spiral into the nucleus. So, electrons undergoing a C should emit radiation, lose energy, and spiral into the nucleus. And Rutherford calculated that this would take about 10 to the minus 5 seconds to occur. In other words, this 10 to the minus 5 seconds, during this time, an electron should give off so much radiation and lose so much energy that it should spiral into the nucleus in 10 to the minus 5 seconds. So the Rutherford model of the atom had two fundamental problems with it, each of which violated a law of physics. Yet we didn't see this happen. The implication of this is that all matter in the universe should cease to exist 10 to the minus 5 seconds after electrons were captured by the atom. But clearly that doesn't happen. So there are some things that must be operating here. The first of these is that two concepts were created to solve the first one, the problem of the protons. The first of those was binding energy. And this is the idea that delta E equals delta mc squared. That some of the mass of particles is converted into energy, and that energy is binding energy that holds the whole thing together. So that was the first model that was put forth. And believe it or not, of course, that was an Einstein thing. The second thing is the strong force. At the strong force, leads to protons attracting each other. Now, we previously learned that the strong force is about quarks attracting each other, but there's a residual or hangover force that comes from that attraction of the quarks that ends up holding the protons and neutrons together. So this problem was resolved. The second problem was resolved by resonance, such that the electrons were particle waves, and as those waves traveled around their orbit, if they were a full number of cycles, they would reinforce each other. So the particle was actually a wave, and as it traveled around, if it were an equal multiple of the wavelength being from here to here, one wave, then it would reinforce each other. So anyway, those were fundamental problems with the model of an atom. But in any case, electrostatic force is about these charges that we already know about. We also know that there is bonding. If we expand our Bohr planetary model, there's something going on with couplets or pairs of electrons, and these different orbitals contain a different number of electrons, and that there is some preferred energy of combination that leads them to be in those orbits, that these two in a pair in this orbit, not next to each other, but the two occupying that energy level creates greater stability than in a different location. The same thing throughout. So the electrical behavior we have is something you already know, of course, and that is there's like charges. Either two positives or two negatives repel. And if we have opposites, a positive and a negative, they attract. So those are that's the first thing about electric force behavior. They can either repel or attract, whereas gravity can only attract. So this is true of these behaviors of the electric are true of particles, charged particles, and charged objects. So in the case, when we think about charged objects, we think about atoms that have protons and electrons, and it's usually neutral. And in case if we remove an electron, it becomes a cation, a positive ion, or if we add an extra electron, it becomes an anion, a negative ion. And so we think about atoms as being charged. But it turns out that objects could be charged. We can have an object, say like this, that's made 10 to the 6th atoms. And so now this is a particle on a vastly larger scale than an atom. This is a particle. And if we remove an electron, or two, or three, or 300 million, since this is such a large object, it's actually a dust particle or smaller. We couldn't see this, it's so small. But compared to the atom, it's very, very large, consisting of many, 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 many atoms. We can remove any number of electrons. This object, then, would be positively charged, which means it would attract both atoms with a negative charge and other particles with a negative charge. Now, in chemistry, the focus is on atoms and molecules. In physics, the focus is on objects. So while it's true, likes repel and opposites attract, when we are talking about objects, either a positive and a neutral, or a negative and a neutral, they attract. So a neutral attracts anything. A neutral attracts either positive or negative charge. And finally, just some things we want to remember about electrical charge. All electric charge results from imbalances of positive and negative charges in the system. Electrical charge, and by that we mean positive or negative, is not a mathematical vector. It's not a vector in a mathematical sense. Positive and negative charge could have been named black and white, just like magnetic charges are north and south, and north and black could be named positive, and south and white could be named negative, or any possible combination. One can also assign, for example, male negative and female positive. And it would seem then that it's become a mathematical property. And we could then apply some mathematics to it and get different answers. But male and female aren't fundamentally a mathematical concept, nor is south and north, and nor is the positive and negative electrical charge. It's just that when there's two, we can use positive and negative, we can sort them out mathematically. And another way to illustrate that, not only with magnetism and north and south, is that the strong force, it turns out, has 3 charges. And it's called color charge: red, green, and blue. And of course, we could try to come up with some mathematical context for that to describe it. But in any case, the charge itself, electrical charge, is not a mathematical or a vector concept. Just want to make sure you remember that. In our next installment, we're going to look at electrical quantities.